In this case study, we will consider linear amplifier design. Linear amplifier design is the basis of all amplifier design. In particular, we will look at the design of an 8 GHz PHEMT amplifier. As well as designing input and output matching networks, we must make sure that the amplifier is stable at low frequencies and high frequencies as well as within the passband. Design begins with a topology in mind, and the circuit shown there has bias inductors L1 and L2. They would normally be very large inductor values allowing DC current to flow through, and the input and output capacitors C1 and C2 prevent the current flowing into the outside world. Not shown here are the input and output matching networks. Now, if we're lucky, we may be able to come up with matching network topologies that will incorporate some of the bias elements. That would be the best result of what we're trying to do. Now, this design is going to be narrow band because we're going to design the matching networks at just one frequency, at 8 GHz. And so the bandwidth is probably going to be around about 8% or so. Well, design always begins with a set of design specifications. So the specifications here are for a maximum gain at 8 GHz. Our topology is going to consist of 3 2-ports, input and output matching networks, and an active device. Of course, this is the topology that we usually have when we're doing amplifier design. But this will be a single stage design, so there's only one active device. We require broadband stability, of course. An amplifier could easily turn into an oscillator if we're not careful. If we only design at 8 GHz and do not consider what is going to happen at low frequencies and at high frequencies, we could very easily design an oscillator. Not a very good oscillator. We actually have to go to quite a bit of trouble to design a good oscillator. It's not the same as a bad amplifier. For bandwidth, we're going to use the bandwidth that's established by 2-element matching networks. That bandwidth is set for us. We could get a bigger bandwidth if we used more elements, of course, and we could narrow the bandwidth as well if we used more than 2 elements. But with 2 elements, our bandwidth is going to be set. And our input and output impedances are 50 ohms. So let's look at the architecture of the overall amplifier. So this is the overall architecture. We have a transistor. Right there in the center we have input matching network and an output matching network. And we have low-pass filters which allow the bias current to be applied. That low-pass filter could simply be an LC circuit. And nearly always there's a bias control chip, an integrated circuit. It could be part of other integrated circuit functions that are already there, or could be a separately provided chip. So that is what we have today. In the old days, we probably would have used voltage dividers, resistor voltage dividers, to establish the bias conditions, but that's not required anymore. So that's our basic architecture, and as much as possible, as I said before, as much as possible, we would like to include some of the special bias circuitry in the output matching networks. And so during the design, we're going to have a number of things in mind. We're going to be concerned about stability. We're going to be concerned about trying to incorporate the bias networks into the input matching network. So here's another view. So we've left the bias network out here. We're going to hope that the bias can be applied through smart design choices on the way through. So we begin with a source resistance. There's our source at the beginning here. There's our source, our load. So we have a source impedance up the front here, which is 50 ohms, a load impedance, which is also 50 ohms. And we also define a gamma S, which is separate from our source resistance. And we define a gamma load, which is separate from our load resistance or load impedance, but they're load resistances at this stage. So gamma S is the impedance that is, or I should say the reflection coefficient seen looking into the input network from the transistor. Gamma L is the same thing looking into the output network from the transistor. The input of the transistor is gamma in. It won't simply be S11, it'll be modified by the other S parameters and the load. And the output reflection coefficient of the transistor will be gamma out. So that's the reflection coefficient we're going to see looking into the output of the transistor. So our transistor is going to have 4 S parameters. It's going to have S11, S21, S12, and S22. A more general configuration of an amplifier would include a feedback network. Generally, that feedback network is only required if we're going to do broadband amplifier design, and it's not required for narrowband amplifier design. It could be used to try and set S12 equal to 0, but often what we encounter with transistor circuits is that intrinsically the gain is high at low frequencies. That would mean that S21, or the magnitude of S21, is high at low frequencies, and the magnitude of S21 falls off, so the intrinsic gain falls off with frequency. So if we want to do broadband design, we need a feedback network which provides a lot of negative feedback at the low end of the band and less negative feedback at the high end of the band. Well, the very first stage is to develop a decision for the transistor we're going to use. Manufacturers provide a lot of useful information. What is shown on this slide is the brief summary information that a manufacturer provides for their transistor. When a transistor vendor is developing a new type of transistor, they're targeting a particular market. In this case, they were targeting a 5.8 gigahertz market. But let's go through this. This is a PHEMT transistor. It's a depletion mode transistor, and we'll talk a little bit about that coming through. The model number. The description they provide is that it's a low noise, high frequency packaged PHEMT. PHEMT being a type of transistor, it's a type of JFET transistor. It's optimized for low noise, high frequency applications. The output is 22 dBm, that's about 157 milliwatts, and that power level is measured when the gain has compressed by 1 dB. So the signal is so large that the gain has suppressed by 1 dB. So we say that 22 dBm output power is the P1 dB power. Of course, we can get any gain from a transistor by providing feedback. But when we go into saturation, the gain that we can get is limited. So this transistor achieves 15 dB power gain when we're at the 1 dB gain compression point. So the gain at 1 dB gain compression is called G1 dB. So the power gain of this transistor is 15 dB at 5.8 gigahertz, but the transistor is usable to 18 gigahertz, and we want to use it at 8 gigahertz. The transistor has 0.8 dB noise figure at 5.8 gigahertz and a 32 dBm output IP3 level at 5.8 gigahertz. And IP3 is a measure of distortion, but we're not designing a high power amplifier here, so we will talk about IP3 in another case study. The transistor can achieve a 45% power added efficiency at 5.8 gigahertz. So it is clear that the manufacturer believes that this transistor is going to work best at 5.8 gigahertz, but some people could use it up to 18 gigahertz. So the vendor will have a lot of different types of transistors optimized for different applications. So this is the first clue that you have in deciding which transistor to use. You look through the manufacturer's catalogs to try and see if they've designed a transistor for your particular application. Now, a PHEMT is a JFET, and the IEEE symbol for the JFET is as shown there. It has a circle around it. It's like a can for a transistor, but the most commonly used symbol is shown there. We usually leave that circle out. Now, those symbols were developed long time ago, many decades ago, and they just simply haven't been updated. So let's talk a little bit about JFETs, and then we'll get on to talking about the PHEMT in particular. So the JFET begins with a semi-insulating wafer, and on top of that wafer, donors are introduced to create an N-type substrate sitting on top of the semi-insulating wafer. And that N-type substrate supports an N-type channel, so we can send current through that N-type substrate. Metal is put down directly on top of the N-type substrate. Here we have a source contact directly on top of the N-type substrate. The junction between the source and the substrate is a Schottky barrier diode, and that is forward bias, so there's very little resistance between the source and the N-type substrate. The gate to substrate interface is generally reverse biased, and the drain to substrate interface is generally forward biased, so it has a very low resistance. Now, we apply a voltage to the gate to create a reversed bias junction. And when we apply the voltage at the gate, or a gate source voltage as we usually call it, the gate source voltage closes off the channel by extending the space charge region into the N-type substrate. And the space charge region has no charge in it. So it looks as though what we're doing is reducing the resistance of the substrate by extending the space charge region into the substrate. So one way of looking at the JFET is that the gate source voltage changes the resistance of the channel. Well, it turns out that that's a good view as long as the drain source voltage is low. But when the drain source voltage, the DS voltage, is high, that reverse bias at the gate changes the drain current. So it does a little bit more than just change the resistance. It changes the drain current. This is called the depletion mode of operation. So without a voltage applied to the gate, there is a conducting channel, current will flow. If we apply a voltage across the drain and source, current will flow. It's only when we apply a voltage to the gate to increase the reverse bias that we start shutting off the channel. So a gallium arsenide JFET is called a MESFET, for a metal epitaxy semiconductor field effect transistor, but we can build JFETs in silicon technology and other semiconductor technologies. So MESFETs are not widely used now. They're largely replaced by a PHEMT operates much the same way. So let's talk about this FET a little bit more. It's a depletion mode FET. So the cross-section is on the left-hand side. The characteristics on the right plot the drain current versus the drain source voltage, and it's called the output characteristic. One of the things to observe here is that when the gate source voltage is 0 volts, drain current will flow if we apply a drain source voltage. At low drain source voltages, it looks as though we have a controllable resistance. As we change the gate source reverse bias, we change the drain current, almost linearly proportional to VDS. So in that low VDS region, it really does look like a variable resistance. But when we get into the large drain source region, we can see that there really isn't a variable resistance here. Now it looks as though the gate source voltage is controlling the drain current. Another way of looking at the FET is to consider what are called its input characteristics. What is plotted there on the left is the drain current versus VG. Turns out it's usually more linear if we plot the square root of ID versus VG. That's a very common thing to do with MOSFETs, and so it tends to be used with JFETs as well. So what we see here, this intersection here indicates that when VG is 0, there is a drain current, there is a threshold voltage, and we operate this device by reducing the gate voltage, making it more negative, putting the gate contact into reverse bias. Eventually we can increase the reverse bias to the threshold voltage level and very little current will flow. So this is called a depletion mode again, because current is flowing even when there's no input voltage applied. And when we apply an input voltage, we shut down the transistor, shut down the current flow in the transistor. There are N-type and P-type JFETs, but always the P JFET. There are N-type and P-type JFETs, but the performance of a P JFET is poor because the mobility of the holes is very low. So designs mostly use N JFETs, and if a P JFET is used, it may be used to control the DC bias currents. Now there are also enhancement mode JFETs. So one of the characteristics here is that there is no current flow when there's no gate voltage applied. Now an enhancement mode JFET takes a bit more effort. It takes a lot of special doping to create this condition, and the doping that is used implements an effectively reverse bias junction even when there is no gate source voltage applied. When we do apply a gate source voltage, as we increase the gate source voltage, we see that current starts to flow. So this is enhancement mode, no current flows without a voltage applied. When a voltage is applied, the current increases. Again, we can plot the input characteristic, and we see that there is a threshold voltage. Must apply a gate voltage, an input voltage above that threshold voltage to get drain current. And if we're designing these, we would like to have very little current flowing when VG is equal to 0. When these are typically used, let's say they're used in a cell phone, for example, we would not want DC current to flow if there's no voltage applied. We want to be able to turn the transistor off. So there's an advantage to having an enhancement mode JFET, but the extra doping required and special profiling of the doping means that it's going to cost a little bit more. Let's compare the enhancement mode JFET and the depletion mode JFET. With the enhancement mode JFET, we see that all the voltages in the circuit are positive. The gate source voltage is always positive, and so that is really quite attractive. We compare it to the depletion mode JFET, we see that we must apply negative voltages, so we need to have an extra supply in order to use a depletion mode circuit. The depletion mode JFET would require a negative voltage to establish bias at the gate. Now PHEMT is a very similar device. The curves look much the same. The difference is that an N-type channel is formed in a very thin layer of aluminum gallium arsenide or a similar compound. And so there's a mismatch with the gallium arsenide, and the effect is that current only flows in the aluminum gallium arsenide. Above that layer is an insulating or a semi-insulating layer of gallium arsenide, and below that is the semi-insulating substrate. So it appears that our gate is creating a reverse bias junction, but it's not quite the same properties. It's affecting the current flow in the channel, but it's not really creating reverse bias junction. But as far as we're concerned as a designer, the characteristics look the same. So depletion mode is what's used most of the time. The enhancement mode is possible, but there are only N-type PHEMT transistors. There are no P-type. So let's just summarize where we've been. There are two modes of operation, enhancement mode and depletion mode. These are the various symbols and names that are used for the JFET. And the fundamental operation of the JFET is one of a voltage, VGS, controlling a current source. So it's a voltage controlled current source, and that is how we think of the amplifier right from the very beginning. Now a transistor vendor provides a lot of information. There are many pages of information for each transistor they're trying to sell, and these transistors can cost tens of cents, so they're not the not sub 1 cent transistor. There's money to be made from these, and the transistor vendor usually provides a reference design. They'll provide measurements for their reference design, and you can be pretty sure they're going to give you characteristics that apply to the best situation. So in this case, the only scattering parameters that were provided by the vendor was at a particular bias condition, a drain source voltage of 5 volts, a drain current of 55 milliamps, and a VGS of minus 0.42 volts. And you can be pretty sure that's the best condition for operation. If this transistor was going to be used in a very large number of cases, the actual designer or the design group would do their own measurements. They wouldn't trust the information from the manufacturer. They would feel that they could do a little bit better. Maybe they'd want to change the bias conditions. So what this manufacturer is telling us by giving us these numbers, they're telling us that this transistor really should be used in Class A operation. So here is a curve. The manufacturer would provide a curve like this. In the middle we have our quiescent point. We have a 5 volt quiescent voltage and a 55 milliamp quiescent current. That's our bias condition. This is the circuit that's being used. It's an inductively biased Class A amplifier, and the output voltage swing is going to range from VDS min, that's the very lowest value of drain source voltage that we can realize, up to twice the VDD voltage. It's going to be biased at VDD, of course. The drain is going to be sitting at VDD when there's no RF signal. When there is an RF signal, LD will be a choke. It'll look like an open circuit. So we must provide a negative gate source voltage of minus 0.4 volts to establish that condition. And again, you can be pretty sure that this is sitting right in the sweet spot of the transistor output characteristics. So this will be a Class A amplifier. The DC power is always being provided. If you multiply 55 milliamps by 5 volts, you come up with 275 milliwatts. And we can compare that to the RF power. The vendor said that the RF output power was typically 22 dBm when we had 1 dB gain compression. So 22 dBm is 158 milliwatts, and when you divide the RF power by the DC power, you come up with an efficiency of 57%. Now we can compare that to the maximum efficiency of a Class A amplifier, which we get using some approximations as being 50%. But that is the efficiency obtained when there's no distortion. We can get a little bit more efficiency if we're prepared to put up with distortion. But all this information, the efficiency coming out around about 57%, the fairly high level of DC bias current, and of course the manufacturer's current voltage characteristic, is telling us that the manufacturer really thinks this should be used as a Class A amplifier. They would have separate amplifiers if they thought this would be useful as a Class A, B or B amplifier. So let's look at the amplifier in a little bit more detail and look at the various classes. So we have typical FET IV curves shown here, but we have two load lines shown. We have a conventional load line that would put our Class A amplifier right in the middle, and a high efficiency load line pulls the load line down. The load line is lower, so this VDS min is a lot smaller, as small as you can get. Now all vendors now recommend that their transistors be used in a high efficiency load line. So you can be pretty sure that the transistor we're looking at here is operating in this high efficiency load line mode. Because this offset voltage here, that one's fairly large, this is fairly small, that is voltage that we can never turn into the RF swing. It is lost voltage. All it does is reduce the efficiency that we can achieve. Now if we look at the input characteristics, sometimes that's an easier thing to look at to see what is going on. This is our Class A amplifier. This is the input waveform. The gate source waveform is a sinusoid, and at the output we will have a sinusoid as well. If we did bias this transistor in class B, very little current flows, maybe just leakage current flows when we have the gate source voltage at its quiescent level, and as the gate source voltage changes, we'll change the output swing, but we'd have a distorted waveform at the output. Anyway, we're operating in Class A amplifier mode here. We're always consuming DC power, but the signal that comes out will have very little distortion. So let's look at the manufacturer's datasheet in a little bit more detail, a little bit easier to see. So there's a lot of information in here. 22 dBm, that is telling us that, allowing for maybe 2 dB of loss in a filter, that the 22 dBm output power here, together with perhaps a 2 dB loss in the filter, is saying that an amplifier using this transistor at 5.8 gigahertz can produce around about 100 milliwatts. If we are using it at its maximum output level, we can achieve a 15 dB power gain. That's a fairly good power gain if that's what we're trying to produce. Usable gain to 18 gigahertz, which is good because we're trying to do it at 8 gigahertz. 5.8 gigahertz is close to a Wi-Fi band and a WiMAX band. That's why that particular frequency has been targeted. It's a bit much to expect that we would find a transistor that's been optimized for 8 gigahertz because that's not a standard communications band. 0.8 dB noise figure is really quite good, so this could be used as the first stage in a receiver. But 100 milliwatts says that it could also be used to send a lot of signal out. So the key thing for us is that it's usable gain to 18 gigahertz. 8 gigahertz is not very far away from the optimized 5.8 gigahertz, so perhaps we could expect similar performance. And the manufacturer gives us the S parameters at a particular bias point, and they only give us the S parameters at a particular bias point. Now there is a model available for this transistor, but when we're doing linear amplifier design, it is much better to use the measured S parameters. They're much more accurate than any S parameters that we would get from the transistor model. So if you are doing linear amplifier design at another bias point, you really should do S parameter measurements. Zooming in on some of the scattering parameters and see what they are telling us. So this is a voltage control current source device. Largely we are looking into the gate when it's reverse bias, so mostly we see a capacitance. So let's see what we can learn from the S parameters. First of all, look at S11 at 0.5 gigahertz. So here I've just taken a selection of the S parameters rather than that busy table, so we're just looking at a few frequencies. At 0.5 gigahertz, S11 is 0.96 and its angle is minus 20 degrees. So on the Smith chart, this is where we are. It's looking very close to an open circuit, and you'll find that if you end up going down much below 0.5 gigahertz, it really does start looking like an open circuit. When we move up to the range where we want to use this transistor, 7 to 9 gigahertz, we're looking at S11, which is around about 0.5, a little bit less than 0.5. And the angle is getting close to 180 degrees, so we're in this region here. So at those frequencies, around about 7, 8, 9 gigahertz, the input of our transistor looks mostly like a resistance. The manufacturer has specifically designed the transistor to be close to being a resistor at those frequencies, at those sweet spot frequencies. So let's move on and look at another S parameter here. We'll look at S21 and S12 provided by the manufacturer. S21 is related to the intrinsic gain of the device. The actual gain of the device will be different from S21 or S21 squared if we're going to be talking about power, because we have input and output matching networks which can be used to do impedance translation, so we actually get some gain from that. But let's look at S21. When we're at 0.5 gigahertz, the low frequency here, we see that S21 is really quite large. Now these are absolute numbers. So S21 here is 11 at 0.5 gigahertz, and it falls off as we increase the frequency, getting down to 1.065 at 26 gigahertz. And so that is a very big drop off. When we look at S12, ideally S12 should be 0. We'd like our transistor to be a unilateral device. It's close to being a unilateral device at low frequencies, but as we go up in frequency, we see that S12 really starts growing. Largely this is because of parasitic capacitance between the drain and the gate of our transistor, and so the drain and the gate is starting to be shorted as we go up in frequency. Finally, let's look at S22. At 0.5 gigahertz, S22 is 0.635. The angle is minus 11 degrees, so it's very close to being an open circuit. So we're looking into the output of our transistor. It's looking close to being an open circuit at low frequencies, which is not very surprising. It's largely a capacitive output. And as we go up in frequency, we see that S22 becomes lower. The angle now is close to minus 90 degrees, where in this region here we really are seeing something that is close to being a capacitor, but it does have a resistive component, and if we follow this line in, bingo, we come to 50 ohms. So the manufacturer has gone to a lot of trouble to try and make it easier to do design so that we do not need very significant input and output matching in order to get this device to work.